complex numbers. Yikes, there's an imaginary component. They couldn't possibly be useful in a real world like ours, right? Well, introducing Euler's identity, which states that e to the ix is equal to cosine x plus I sine x. You might be wondering, how is this possible? A transcendental raised to an imaginary somehow becomes a simple complex number? Well, let's prove it using Taylor's series. We first plug in ix in the e to the x series. Then, we rearrange the terms and evaluate the I exponents. Finally, we can plug in cosine x and sine x for their respective Taylor series. We can also derive other forms of Euler's identity, such as the following two formulas for sine and cosine. Now, let's use what we learned in a real-world application: circuits. This type of circuit, called an LRC circuit, can be modeled by this differential equation. We will only evaluate the homogeneous solution in this video. That is, we set the differential expression to 0. We then assume a solution of the form q of t equals e to the rt. We can then arrive at these deductions. Now we have three cases. Let's consider the complex solutions case. We've now obtained q1 and q2. Let's tidy this up by assigning phi of t to the imaginary part. In diff and q, if two functions are solutions, then a linear combination of the two is also a solution. Finally, we can apply Euler's identity to obtain real solutions. So play around with complex numbers. You might just make the next breakthrough discovery.